Cool. Okay, so topic 1 is quantitative chemistry or stoichiometric chemistry. So this is all the mathsy stuff about moles. I'd say the most important thing is limiting and excess reagents. I'd love to catch you out on this. At standard level, they tend to be a little bit nicer and they tend to actually tell you that there's a limiting and there's an excess reagent. At high level, the biggest tip I can give you is that they might not outrightly ask you to find the limiting and the excess. What they'll do is they'll give you masses for the starting materials, and that's your clue. So you really need to be on your guard. If you get masses for the 2 starting materials in the equation, that means figure out your limiting first and then do the rest of the calculation. Standard level, as I said, they tend to be nicer. The other thing is remember the difference between your empirical and molecular formulae. So your empirical formula is the simplest ratio, but the molecule won't necessarily exist as that simplest ratio molecule, whereas the molecular ratio is the actual ratio in the molecule. And you'll have to calculate that from either the mass composition or percentage composition, that kind of thing. Concept of the mole, you'll get maybe 1 or 2 questions, not a big thing. Ideal gas laws, again, small thing, so not something to stress about. Topic 2 in general isn't red at all. By the way, my color scheme, red means it comes up a lot, and italics means it's high level. So topic 2 is a really, really small topic. You should be able to revise it quite quickly. And because it's so small, it just doesn't come up very often at all. I'd say the biggest thing here is the emission spectra. So really understand why the emission spectra shows that electrons live in shells. Just from a chemistry point of view, that's just quite a groundbreaking discovery they did there from quite literally some colored lines on a graph. But aside from that, I really wouldn't spend that much time on topic 2. It's not worth it. Paper 1 questions, there aren't that many of them. And paper 2, there are even fewer. They might sneak a couple in, like where you have to calculate the relative atomic mass, but I'd say that's pretty much about it. Cool. Topic 3, periodicity. So this is probably quite a dull topic in all honesty. It doesn't require that much understanding. The crux of this topic is just when electrons are further away from the nucleus, there are more shells, so there's more shielding. And so basically what that means is that then the electrons aren't held in as tightly. And that will have effect on radius, on electronegativity, reactivity, everything. So that's basically the basis for everything. The important thing with periodicity is to know all your patterns, but also just to be able to explain them. And in the exam, some people just tend to waffle. A lot of students waffle and they think, oh, the more I write, the higher the chance I'll get the score. In reality, I would recommend that you just write them in bullet points. The examiners won't mind. You're never marked down for writing in bullet points, and it'll just mean you're much more succinct and you're not having, you're not going to waffle basically, and so you're more likely to get the marks. Transition metals for you guys out there who are high level, I would say those are really the important part. Yes, you'll be asked on the trends, especially in paper 1. They'll be like, okay, it's moving across period 3. What's the most acidic? I don't know, oxide or chloride or whatever. But your transition metals are super important because it's very different. It's very difficult. They form colored complexes. The reason they form colored complexes is because the d orbitals are splitting in energy, and it's kind of the first time you've ever encountered that. So I would highly recommend making sure you know your transition metals inside out and the reasons why they form all these colored things, basically. Okay, topic 4. Title is in red because it is, I would say, the most important topic on the entire chemistry syllabus. It's a very core, basic topic, which means it comes up a lot in exam questions. It sneaks up everywhere. So you might have an exam question that starts off with a bit of organic, then goes into some bonding, then maybe goes into some quantitative, but bonding always tends to be mixed up in there. And the important type of bonding out of all of them is by far covalent bonding. So you really, really, really need to be comfortable drawing Lewis structures. Remember, you've always got to put in the electrons, you've got to put in the charges. Remember, most atoms just want to form a full shell with 8 electrons. So I really recommend that. In terms of intermolecular forces, one trick here is if you ever have a question on boiling points and melting points, always think of your intermolecular forces. So does it have London dispersion, dipole, or hydrogen bonds? Because basically the sneaky way of the IB asking you about intermolecular forces is asking about boiling points and melting points. They won't necessarily outrightly ask you about the intermolecular forces of a molecule. Allotropes of carbon, tiny topic. I mean, remember it for paper 1, but not much else outside of that. And then for the higher levels, hybridization tends to instill fear in people, unnecessarily so, in all honesty. All you need to remember is the definition. So it's all about the mixing of orbitals to make hybrid orbitals. Now, the reason we do it is purely a model. So we know that molecules form, say, a tetrahedral shape. If we take methane, it forms tetrahedral shape. And we know it uses the s orbital and the p orbitals. But basically, if you put the s and the p's together, it doesn't make a tetrahedral shape. And so that's why we hybridize everything, so they're all sp3 orbitals. I'm not going to go into detail, but all you need to know for hybridization is a definition, and you need to be able to work out sp, sp3, sp2. So someone wants some diagrams for hybridization, but yeah, this is a current problem, sadly, because I'm on my laptop. I can't draw anything. I wouldn't say you need to draw diagrams for hybridization, okay? So the way I remember it is, let's say you've got ethene. So ethene is 2 carbons with a double bond in between them. So if you look at each individual carbon, it's bonded to 1 other carbon and 2 hydrogens. So it's bonded to 3 atoms in total, which means you have to mix 3 orbitals. So you're going to mix 1s, you always mix 1s, and you only need 2 more orbitals, so you'll mix 2 p's. And so in ethene, your carbons are sp2. If you go to ethyne, which is 2 carbons with a triple bond between them instead, each bonded to hydrogen, if you look at each individual carbon, it's bonded to 1 carbon and 1 hydrogen, so it's bonded to 2 atoms, which means it needs 1s, and then it just needs 1 more orbital, which is the p. And so there it's sp. And lastly, if you look at ethane, so the alkane, where everything's just single bonds, each carbon is bonded to 3 hydrogens and 1 other carbon. So it's bonded to 4 atoms. So they all mix 1s and 3 p's. So basically, all you're really looking at is how many atoms is this carbon bonded to. That's how many orbitals you need. You're always going to have 1s, and you just add the extra p's, basically, to make up the number of atoms it's bonded to. Hang on, another question is being written up in terms of hybridization. Does dsp3, as in with d orbitals? No. You only need to know sp, sp2, and sp3. Once you start mixing the d's, it gets super complicated. And they're realistically only really going to ask you the hybridization of carbon, which means the highest hybridization is sp3 anyway, because it can only form 4 bonds, so it can only mix 1s and 3 p's to make 4. So don't worry about d orbitals at all. Okay, any last minute questions on hybridization before I move on? Post now or be silent forever. Oh, the suspense is killing me. Okay. Well, if you've got more questions, ask away and I will answer as I go along. Trickiest thing of bonding, for sure, is hybridization. So if it's something you struggle with, just do definition and just learn how to figure out sp, sp2, and sp3. All you need to know, don't worry about actually understanding what it is if you don't have the time. It is not your priority. If you want to be a chemist, you can learn it later. Cool, okay. Topics 5, 6, and 7. So this is kind of thermodynamics and equilibrium, and some kinetics as well. So topic 5, in terms of Hess cycles, so the first thing you've got to do is calculate enthalpy change. This is both standard and high level. In terms of Hess cycles, you rarely actually have to draw the cycle. So if you have a method where you just flip equations, just use that method. It's foolproof, it's fairly easy, you're not going to get it wrong. Bond enthalpies and calorimetry tend to fill people with less fear, so it should be fine. Entropy is quite straightforward. You just have to always remember the definition. So remember, entropy is a measure of disorder. So basically, the more positive an entropy is, the more disorder is present. And spontaneity just basically links together entropy and enthalpy. There, the only thing you really need to learn is your Gibbs free energy equation. So delta G equals delta H minus T delta S. Things to point out there: remember this equation, memorize it. Don't rely on your data booklet because you'll have to use it in paper 1. The other thing is your units. So Gibbs energy, delta G, is always in kilojoules per mole. Enthalpy is in kilojoules per mole, but entropy tends to be in joules per Kelvin per mole. So you always, always, always need to remember to change entropy into kilojoules. The last thing is your Born-Haber cycles. Again, this is like hybridization, tends to fill students with fear. I don't blame you. I hated it when I did it. The only thing I can really suggest is to do it stepwise. So basically, you always, let me think, you always atomize everything first. So make everything into gas and make it all individual molecules. Then you ionize it. So first ionization, then second if you need it, and third if you need that. Then you do electron affinity. So that's when the other atom is then gaining those electrons. And then you do your lattice enthalpies. And that's how you create a cycle. And you connect it with enthalpy of formation. I know this is all hard to visualize with no diagram, but I'm just trying to give you as many tips as I can in this hour to help you with your revision. Okay, kinetics tends to be fairly straightforward, really doesn't come up at all, much at all. For standard level, it's literally just what is collision theory, what is a rate of reaction, and what are the factors that affect the rate. So the factors, remember, are temperature, surface area, concentration, pressure, and a catalyst. I remember with Tesco PCAT, if that helps anyone, a bit of a wacky way that my teacher showed me. For high levels, it then gets a bit tricky, calculating orders of reaction from experimental data. That could crop up in your paper 3 as potentially an experiment. Arrhenius equation is the other thing. Like your Gibbs energy, do memorize the Arrhenius equation. Don't just count on your data booklet. What was I gonna say? Oh yeah, and when you're plotting the graph, always remember your line has to have a negative gradient, always. Okay, and then the last thing is topic 7. This one's tiny, this one really doesn't come up much. For standard levels, just make sure you know Le Chatelier's pretty well. So if I change something to the equilibrium, it's gonna go one way or another. For high levels, I would really focus on equilibrium calculations because they're the tricky ones that can catch people out. I use the ICE method, which is basically where you calculate the initial, the equilibrium, and the change in between. If you have another method, go for it. It works just as well. Cool, okay. Then topic 8, acids and bases. Another one, from now on, basically people don't like topics, is what I've gathered. I hated acids and bases. I absolutely hated the calculations, but you don't know how important they are. Buffer solutions, especially at high level, tends to catch a lot of people out with the calculations. All options have buffer calculations in the high level. So there's no way you can get away from it. In all honesty, I think that almost definitely going to ask something about a buffer calculation in your paper 3. So I really make sure you're happy with them. My biggest recommendation for this is to go through a lot of past papers, because basically when I was preparing for the first time to tutor, I was really worried about tutoring these calculations because I wasn't very good. And all I did was a load of past paper questions, and you realize just how similar they are. And they literally just change a few numbers and that's it. So it's all about calculations. I would split it like this. I would learn how to do strong acid base calculations and what equations you need there. So like pH equals negative log of H plus. Then I would do the weak acids and bases, which brings in some equilibrium knowledge. And then I would do the buffer solutions afterwards and kind of tie everything together. As for the rest, fairly straightforward. I wouldn't really stress about it. This acid deposition thing is new, but it's just a lot of information. It's kind of all about acid rain and all that stuff. It's just memorizing. If you memorize it, you'll be fine. Next one is redox. Redox numbers are tough. Writing redox equations can also be tough. Again, just be methodical. If you've got a sucky teacher and you're really lost with redox, there must be resources online to help you, because redox numbers literally just have a certain number of rules and that's it. And from then, and writing equations also just have a certain number of rules. So shouldn't be a problem. Winkler method is new. Now this I think will really crop up just because it is brand new. It involves some of your knowledge from topic 1. And yeah, it's not too difficult. It's just remembering all the equations, the order of the equations for the Winkler method. But it's worth, I think that one's very much worth learning. And then you've obviously got your electrochemical and your voltaic cells. Out of those two, I'd say the voltaic is really, really important, especially if you're higher level, because it's got all this stuff about spontaneity, which will then link to topic 5. So the question could then either go from topic 5 to topic 9, or standard electrode potentials as well, which just requires a little bit more understanding, basically. So I'd say they're the really important ones out of that. Cool, and then we get to topic 10. In all honesty, the biggest things here are all the reaction mechanisms that you have to learn. You have to learn to be very comfortable with drawing arrows, what the arrows mean, especially at high level, and yeah, and just be comfortable with those equations, basically. Yeah, okay, questions are coming my way.
Okay, acids and bases.
Yeah.
Do you need to calculate the pH of salt?
You don't need to
Salt.
Okay, you don't need to calculate the pH of salt hydrolysis equations. Basically, salt hydrolysis is just, they'll give you a salt, so for example, NaCl, and you don't have to calculate the specific pH, you just have to say whether it's basic, acidic, or neutral. With an example like NaCl, you can, the easiest way I think is to think, okay, how was NaCl made? So that was the reaction between sodium hydroxide, NaOH, and hydrochloric acid, HCl, will make NaCl and water. Sodium hydroxide is a strong base, hydrochloric acid is a strong acid. They're going to completely neutralize each other. So NaCl in this case would be neutral. That's all you have to do in terms of hydrolysis, salt hydrolysis.
Okay.
Cool. Next question.
Is there an easy way to figure out the Winkler method?
I don't know of a particular.
You have to memorize all the equations for the Winkler method.
Yeah, I don't know a particular easy way to do the Winkler method. You do just need to memorize the equations. There are only 4 of them, I think. Last time I looked. So it's a pain in your butt, and I get that. But no, I wouldn't say anything easy.
What is Tesco PCAT for?
Okay, so Tesco PCAT, I did rush over it. Basically, in topic 6, when you're doing factors of rate of reaction, so the Tesco, actually I can type this, which will be easier so you can read it. Okay, so TE is for temperature. Then you've got S is for surface area. Then CO is for concentration. And the P is for pressure. And the CAT is for catalyst. So Tesco PCAT. So you won't forget anything. But that's basically all there is to it. It's just to remind you of all the possible factors.